Okay, so let's talk about exponential functions. Um, Exponential functions are very, very fundamental to math because so many things in real life are modeled by exponential functions, right? So exponential functions are power functions where the base is a constant and the exponent is a variable, right? So for example, here f of x equals 4 to the x, 1 over 3 to the x, 7 to the negative x. All of these are exponential functions, constant to the power of a variable. Okay, here we have some more exponential functions. Like e to the power of x minus 1, that's an exponential function. Basically, the main characteristic of an exponential function is that it has a very, very rapid change, right? So if you go over horizontally just by a little bit, you go up or down a lot in comparison on the y-axis. Okay, so some things that are modeled by exponential functions, right? Like the spread of like germs is an exponential function, right? I mean, I always give this example where like, okay, it's like January 2, you come to school and you've missed all your friends and you hug everybody, and then all of a sudden like you're not feeling well. Well, lo and behold, your friend was sick, they coughed all over you, and then like within hours, you're just like, I feel so, horrible. That's exponential growth, right? Like the bacteria like grows exponentially. Then you go on some antibiotics, and then like this, you're feeling better again. That's exponential decay, okay? All right, you've heard that story before. So, here are graphs of exponential functions. The first we're gonna look at is exponential growth. And do you see how, it basically, when you read from left to right, the y values are increasing, right, as you move along the x-axis. So basically what's happening is as x approaches positive infinity, right, f of x, the graph is moving away from the x-axis. So that could be going upward or downward, okay? That would be growth. The domain of all exponential functions is always all real numbers. The range in this case is from 0 to infinity, or if it goes below, it's going to be 0 to negative infinity. And then, we can figure out the end behavior. All exponential functions are continuous from negative infinity to positive infinity. The most important thing is all exponential functions have a horizontal asymptote, okay? So if this was y equals 2 to the x, is there a value of x that would make this 0? No, right? That's why there is a horizontal asymptote there. So the range is going to be starting with the horizontal asymptote, going up or down. Now, if I have exponential decay, as x approaches positive infinity, the graph moves toward the asymptote or the x-axis, okay? In this case, I'm just going like with the default, the parent function, it'll move toward the x-axis. Okay, the domain again is all real numbers. Same idea with the range and so on, okay? Now, that's how you can tell from a graph if something is exponential growth or exponential decay. What if you had this, by the way? Is this exponential growth or is this exponential decay? Is this growth or decay? Growth, because as you move towards the x-axis, it's moving away from the x-axis, right? So this is like you're growing into the negatives. So imagine if we were talking about like somebody's debt, if you were talking about like the national deficit, right? The country owed this much money and then the debt grew. Now you owe like trillions of dollars, right? Okay. So that's how you can tell from a graph. But if you have the function, it's exponential growth if this number b is greater than 1 and it's exponential decay if it's between 0 and 1. All right? So take a look at this first one, 2 to the x. Is this growth or decay? Growth. What about 0.5x? Decay. What about 1 over 3 to the x? Decay. What about this next one? Okay, so here we have 1 over 4 to the negative x. That means this will be 4 to the positive x, so it will be growth. Okay? All right. If you have, y equals 3 times half to the power of x, this is still decay because this is b. This is what's being raised to the exponent, so it'll still be decay. Okay? Yeah, it's the value, it's the constant that's being raised to the variable exponent. Okay, so to graph a function,
let's say it's like 3 over 2.
That's growth because 1.5 is greater than 1. Yeah. So to graph, okay, so first we have to figure out what the asymptote is. Now in the default case, when there is no vertical shift, the asymptote is always y equals 0. Okay? The y-intercept is f of 0, which is 2 to the 0, which is 1. So 0, 1, right? And then to graph, I quickly just mentally plug in a couple of values, okay? So usually, if it's growth, I like to pick these numbers. You can't pick too many big numbers because the values get so big so quickly, right? So here, 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. So here, negative 1 is first the asymptote. Don't get caught drawing one of these without an asymptote, right? 1, and then 2, and then 4. Okay? And, we got to go up that way and here. Okay? Now, you can do this mentally, right? Because this is 2 to the power of. So what are the powers of 2? 2, 4, 8, right? And then the other way around, it's 2, 1, 1/2, 1/4, 1/16, right? So you should be able to just rattle them off like that. Yeah. B won't be 1. It's usually an exponential function. B is not 1 because then it's just 1. Yeah. It's greater than or less than. Okay, so the domain is always all real numbers. There is no math involved there, no thinking involved there. The range is 0 to infinity, always open. As x approaches negative infinity, we go to 0, and then positive infinity goes to positive infinity, continuous everywhere. Right? Okay. Next, 3 to the negative x. Now this is the same as 1 over 3 to the x. Yeah? So asymptote is still y equals 0. Y-intercept still 0, 1, because anything to the power of 0 is 1. Okay, so when I have a decay like this, I like to shift to the left one so the numbers don't get too big or too small. So I like to go from -2 to 1. This is not the law. It's just like good practice, okay? That's all. So when x is -2, this is 3 to the power of -2, which is 9. When x is -1 is 3. Then 0, and then 3 to the -1 is 1/3. Okay, asymptote. Oh, I forgot to mention about your finals. At -2, we're at a 9, then 3, then 1, then 1/3. You see, beautifully decaying, okay? Domain is still all reals because, range is 0 to infinity. As x approaches negative infinity, this goes to positive infinity, and then 0, and it's continuous everywhere. Okay? All right. Transformations work in the same way. Okay, so basically, look, if you have 2 to the power of x plus 1, this moves the graph to the left 1 unit. Okay, if you have, 2 to the negative x, this is a reflection around the y-axis. Do you see how the reflection around the y-axis changes back and forth between growth and decay? Isn't that cool? Coolest thing you've heard in 2024, right? Yeah? Yeah. So, yeah, right? But this is the coolest. No? Yeah. Yeah, for sure. Yeah.
So 2 to the x plus 1 doesn't matter.
Huh?
What is the 2 to the x plus 1?
It shifts it to the left 1 unit. Okay? And then if you have a negative out front, this is a reflection around the x-axis. But notice here, growth stays growth, right? Okay. All right. Natural base. Natural base is an E, remember? Okay. So, most real-world applications involve not 2 to the x, 3 to the x, but e to the x. E is the natural base. Now, what is E? Okay, there is this term, this term here, 1 plus 1 over x to the power of x. 1 plus 1 over x to the power of x. This term shows up a lot in a lot of like calculations, formulas, derivations, and so on. It's just a very, very common thing. And often we have to look at what happens to the limit as x approaches infinity of that. So when you graph 1 plus 1 over x to the x, it actually, like, the graph of it like looks like this, and then it levels off. At infinity, guess what value it levels off at? 2.71828, blah, blah, blah. So that has become known as E. Okay, so that's where it comes from. To graph E, same exact thing, but, usually these are calculator questions, right? Asymptote is still y equals 0. Y-intercept, e to the 0 is still 1. And then this is still growth, so I use these same numbers to graph these. So here, huh? No, and actually, I don't need you to create a table for me when you're graphing this, okay? All I want you to do is on your calculator, just graph e to the x and then just like transfer the values here, okay? At this point, honestly, like no one's going to be asking you to put in values, okay? So e to the 0 is 1. E to the 1 is 2.7, right? And here is the asymptote. So basically, all you need is 3 points. E squared is 4.7, because doesn't everybody know that? Right? That's all you need, really. And then this. Okay? My concern isn't for you guys to be able to graph this on your calculator. My gosh, like you all know this, right? Again, the domain is all real numbers. What the heck is going on here? Exit. Huh? But when you graph it on your calculator, Ben, just like go to where x equals -1. No. There is an E button on your calculator on the left-hand column where there is ln and E. Please never put the rounded one. So domain is all real numbers, 0 to infinity, and then these you guys know, right? Do I need to go over this? No. Okay, let's go ahead and do this one. So e to the 2x plus 3, go ahead and graph this quickly. Here for this one, before you even graph, take a look. This +3 moves everything up 3 units, including the asymptote. So now for the first time, the asymptote is y equals 3, okay? And the y-intercept, f of 0, is e to the 0 plus 3, which is equal to 4. So 0, 4, okay? That you should be able to do without even a calculator. And then once you have this, I like to go into trace mode, menu, trace, graph trace. Now in here, let's say I put in -1, enter, it's 3.14, okay? You don't have to make a table, but you need some like precise points, right? So this is what I do. Okay, -1 is 3.14. So I go here at -1. Here is my asymptote. Okay, look, let me escape this. So you go menu, trace, graph trace, right? And here I can put in any value. So I'm just going to type in 2, enter, and it's 57.6. I'm not going to graph that. I'm not crazy. 1, enter, 10.4. All you need is like 2 or 3 points for me, and then you have like a multitude of points. Just pick ones that like work within your range, okay? So at 0, this was 4. Just type in 3, enter, in trace mode. Yeah? Okay? And you guys are good with this? Yeah. Okay, so let's move on to some good stuff. So in previous years, you know, this is where you would do, let's say, what was I going to say? You know, like compound interest and stuff, but I'm not going to bore you guys with that. Okay, so compound interest is one place where you use this stuff. But in addition to investments, other fields can change at an exponential rate, right? This includes populations of people, animals, bacteria, or amounts of radioactive material, okay, half-life, and so on. These are all exponential decay. Now, here is where notation comes into play a little bit. Your book, for some reason, uses N and N naught, which nobody else in the world uses. Everybody else in the world uses Y and Y naught. So here I've put both versions. So N naught, okay, that's subscript 0. Have you used that before? Yeah, no, yes, no. Yeah, why not? Yes. So whenever you have a subscript 0, it's called like blank not. You know, why not and not? That always indicates initial quantity. In this case, okay, so take a look. You have exponential growth or decay. The formula is y equals y naught 1 plus r to the t. Okay? Your book uses n and n naught. I like the y's. R is a growth rate, okay, if r is greater than 0. And then it's a decay rate if r is negative. So if this was, you know, plus 0.2, it's growth. Minus 0.2, decay. All right? Now, if there is continuous exponential growth or decay, then this is the equation, y equals y naught e to the kt. Okay? And in this case, instead of r, we use k. Okay? Yes? Huh? T is time. So the one to the right is continuous, and it has to say like it grows continuously. Okay? So for example, like salaries, if your salary increases by a fixed rate every year, that's not continuous. That's like an annual growth. You would use the first one to the left. Okay? But if it says something is changing continuously, then you would use the one to the right. Okay? So take a look at this one. A state's population is declining at a rate of 2.6% annually. This is now the first one to the right, to the left. The state currently has a population of approximately 11 million people. So R is equal to negative 0.026. Y naught is 11 million. If the population continues to decline at this rate, predict the population of the state in 15 years. T is equal to 15. So y equals y naught, 1 plus r to the t. Y is 11, 1 minus 0.026 to the power of 15. Here's what I found. Oh my God, dude, This person has been listening to me all day. Okay. So y would be 7.4093. Okay, so in 15 years, what is the population roughly? 7.4 million. Okay, so 7.4 million. Okay, yeah.
You expect to memorize the.
Yes, everything here you need to memorize. Yep. You can't, by the way, you cannot go through calculus without knowing this. It has to be like second nature. It's like, what's your name? Todd. What's the exponential growth formula? Y equals y not e to the kt. It's like that.
And you knew it was exponential because you said annually.
Yeah, usually if it's a annually like this, right? Because it's like times 2.6% times 2.6% times 2.6%. So it ends up being like 2.6 to the power of x. It would literally say at a continuous rate of blah 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 annually. Okay.
Even though it says that the population continues to decline.
Where? Yeah. It would be here. Like here, it would say it would be declining at a continuous rate. Yeah. Mm-hmm. Okay, so uranium-235 has a half-life of 704 million years. Okay? Write a modeling equation for the exponential decay of uranium-235. So do we know what half-life is? Half-life is the time it takes for half of something to decay. So for example, if you start with this much uranium, and let's say the half-life is 704 million years, in 704 million years, this much of it will have got like decayed away. In another 704, half of that would have decayed. In another, okay? So now we need to write a modeling equation. Whenever you're dealing with half-life, this is y equals y naught e to the kt. This is always exponential growth, continuous exponential growth. You need to know that. So for part A, we're going to use t is 704 million. Okay, so we need y equals y naught e to the kt. What we need is the growth rate, is the decay rate. We need k first. So y naught, okay, is the initial value that we have. Okay, so here is the equation. Y equals y naught e to the kt. So when we start, we have y naught e to the k, and t is 704 million years. Okay? Now, after 704 million years have passed, how much of the stuff will remain? Half of it. So half y naught. Okay? So if y naught is the initial, half y naught is the final amount. Okay? So now, what happens to the y naughts here? They go away. So what I have here is half equals e to the 704k. Now, how did we get rid of all this? ln of both sides. Yeah? So now I have ln of a half is equal to 704k. K is ln of a half over 704. Huh? Yep, and then put it in the calculator. So K is negative 9.846 times 10 to the negative 4. Or negative 0.000986. Okay? Either way. So now, my modeling equation is y equals y naught e to the negative 0.0009846 t. Okay?
You have to write it out like that?
Yeah.
We can't just do the scientific notation.
You can do scientific notation. Oh, yeah, sorry. You can do scientific notation. I thought you meant the equation. Right. Okay? Now, let's actually put this here. Let's actually all put this here for a minute. Olivia, you okay? Okay, so here we have ln of a half, okay, over, what is this? 704. Okay, that's what we get. Now, take a look here for a minute. I don't want you to keep rounding, please. I'm going to take points off if you keep rounding for the next parts in semester 2. So let's go to part B. Part B says how many grams of uranium will remain after 2 million years if we start with 300 grams. So part B is y equals 300 e to the, this is the 46 times 2 after 2 million years. So y equals, let's put this in, 300 e to the power of, now you need to put this value in there, okay? So you're going to do set control answer times 2. You're not going to round it in your calculations because it will give you a different answer, okay? You're going to use the whole thing. Equals 299.4. Okay? Grams. Huh? You're plugging that into your calculator. Instead of rounding, you're just going to do like control answer. Put control answer here. Okay. Next. Use your model to estimate when 200 grams will remain if you start with 300 grams. So, for part C, you want y naught to be 200. You start it with 300 e to the negative 0.0009846 to the power of t. Okay? You divide both sides by 300. So you get 2/3 equals e to the, that crazy number, t. Now ln of both sides. So ln of 2/3 is equal to that crazy number times t. So now I have to divide. T is ln of 2/3 over this. So go back to your calculator. Look, we're going to do ln of 2/3 divided by, what was the number? It was this number, right? Here's how I go back to that number very quickly. Just, scroll up, hit the up button, highlight that, press enter. Look, it gives you back that number. Press enter, and you have 411.8 years. Oh my God. Oh, million years. Wow, first big time mistake of 2024. Oh, wow. Didn't see that. Just write million years, man. Jeez. This is all I've been at. You're really gonna... 3 letters. Ion. Okay, go.
So we can't put the 0.0009846 in the calculator?
No, don't round it. Use the whole thing, unrounded. Okay? Questions? All right, let's do this one quickly. So this table shows the number of reported cases of chickenpox in the United States in 1980 and 2005. Okay? Very interesting data. Huh? Hopefully it went down. Well, I don't know. Did it? Ooh, it looks like it did. Look at that. Look at what vaccinations will do. Okay, but I digress. Okay, the number of reported cases of chickenpox is decreasing at an exponential rate. So we need to identify the rate of decline and write an exponential equation to model the equation. All right, so we are definitely going to need our calculators for this. So it's declining at an exponential rate. Now, it's not saying it's a continuously declining rate. So we're going to use y equals y naught, 1 plus r to the power of t. What we need to find is the rate of decline, which is r. Okay, so the final amount is 32.2, equal to the initial amount, 190.9. 1 plus r to the power of how much is t? 25. Okay, so divide by 190.9, so we have 32.2 over 190.9 is equal to 1 plus r to the power of 25. Yeah, y equals y naught. Y is the final. Now what am I going to do? Take the 25th root, because why not? Okay? Yeah. So let's go ahead and plug that into the calculator. So let's see. The 25th root. Is that what it is? Let's see. Is it 25? Oh, man. And here. Is that right? Plus I have that extra 5 over there. Okay. So, yeah. So 0. What was it? 9. What was it? Is equal to 1 plus r. And so r is, that minus 1. Again, never round. So just do minus 1 equals this. So it's negative 0.069. It doesn't say what number to round, how many decimal places to round to on the test, and because I'll always specify. Okay? So this is the rate of decline. Okay? And is it right for it to be negative? Yes. Use the model to predict when the number of cases will drop below 20,000. Okay? So for this one, here's what we're going to do. What was the equation? It's y equals, what was the initial amount here? 190.9 times 1 minus 0.069 to the power of t. Okay? So now I go to my graph. Let's get rid of this. And that's what I'm going to graph over here. 190.9. That is not 190.9. Times 1 minus 0.069 to the power of x. And obviously, I'm not going to be able to see anything, but I want to see when it drops below 20,000. So in this F2, I'm going to put in 20,000. Okay? So now, 20,000. Huh? So here, I'm going to change this to 20,000. Okay? Oh, wait a minute. Oh, because this was in the thousands. Sorry, I'm sorry. This was in the thousands, so I'm going to go to 20. Sorry. So let's go to 25. Why doesn't this? Okay. Okay. What happened? Oh, I don't know what you graphed there. I don't know what you graphed there. Okay, so here, when is this going to happen? Let's go to, huh? Okay, here we go. It's 20 because the numbers are in thousands. So if I wanted to drop before, yeah? Yeah, 190,000 and so on. So here, look at this. That's the intersection, right? So the graph is coming over. At this point, it drops below 20,000. And if I go over and I find that point of intersection, it's 31.6. So T equals 31.6. What year is that? Yeah, it's like about 32 years. So when the number of cases, so it's either like after 31.6 years. So after 32 years. So when would it be? 2012, 11, 2012, yeah. So after 32 years. Okay? Isn't that cool? Yeah. Oh, okay. All right.